Our next speaker is Benedetto Scoppola from Rome. He'll speak on randomized algorithms for the maximum clique problem.
Thank you very much to the organizer for inviting me and for the possibility to give this talk. This is a joint work, and we were in the beginning three with Antonio Ioanella and Elisabetta Scoppola, and then Alexandre Godier and Maximiliano Viale joined us. The first part of the work is already published, but it contains most of all numerical results, and we are still working on the second part I'm presenting you today. Well, let me start with maybe two well-known things. I don't know, but I'll start with well-known things anyway. And we have a graph. The problem that we want to study is to find the complete subgraphs of this graph, and in particular the complete subgraph with the maximum cardinality. The cardinality of the maximum clique of any maximum clique in G is the clique number of the graph. A possible way to quote this problem is to say, for a fixed k, are there any complete subgraph of that size? I will talk about a related problem, maybe if I'll have time, in the end of the talk. And this problem is the balanced complete bipartite subgraph problem, which is if you have a bipartite graph, you want to find a subgraph which has the same number of vertex in the two parts of the graph, and such that all the vertex are connected each other. This can be reduced to the clique problem and is in the list of the Gary Johnson book. In this seminar, I will focus on the problem to find the maximum clique, to find the maximum clique of Eidos-Rangi random graphs, and a random graph with the fixed density D. Here, D is the density of the graph is not dependent on n, so one has to expect that any vertex of the graph has order n neighbors, as degree order n. When you have a random graph, there are a lot of results about the clique number, and they start from the observation that the expected value of the number of the complete subgraph of cardinality R can be computed and is n choose R times D to the R choose 2. And this can be approximated. The rough approximation you find on the screen is very rough, but is enough to see that if you want to find the number R such that this expected value of the number of cliques is roughly 1, this number R is of the order of the logarithm of n. In particular, is twice the logarithm in base b of n, where b is the inverse of the density. It turns out that, in fact, around this value, one can find the clique number of the graph with very large probability. More precisely, one can find these well-known results, for example, on the book of random graphs by Bolobas, and these results shows that the clique number is very the distribution of the clique number of a random graph is very narrow. It has a finite width, and in fact, if n is large enough, you with probability 1 in the sense that you can see. I mean, you take a graph on an infinite number vertex, and then the set of subgraph with n vertex have the clique number equal to R0 of n with an error smaller than 3/2, almost certainly. So if you pick at random a random graph with of order n, you find that the maximum clique number is R0 of n with very high probability. Well,
I'm lost with the quantifiers here. What? Almost all the graphs G.
For almost all,
What is GND? Is that an infinite?
GND is an infinite random graph. N is matbb is the set of is a natural number.
But did you need to state it this way? Aren't you just saying for almost all random graphs GN?
Well, this is easier in the sense that it's a way to state the result in terms of measure one. Almost all it means if you choose a random graph defined on the set of on an infinite set of vertex at random with probability 1, you find a random graph such that with probability 1 a subgraph as the clique number very near to R0 of n. If you want, you can quantify this, and it has been done. In fact, you can quantify this in the sense that if you fix an n, you can study the probability to have a difference between the clique number and R0 of n bigger than 3 and by 2. But this is the simplest way to state the result. Anyway, the message is clear. If you pick at random a graph, the clique number is roughly this complicated, but not too complicated expression. As you see, is twice the logarithm base b of n plus corrections. Well, if you want to find the maximum clique, for example, of a random graph in this seminar, there are two different families of algorithms. You can explore the whole graph, and even if you do it in a clever way, you spend a very long time exploring the whole graph, trying to find the largest clique. And typically, you can study with the complete methods, just small graphs, or you can study heuristic methods. Heuristic methods, it means that the result that you obtain, of course, is not optimal, but if you are in some sense lucky, and we will see what does it mean, you find a clique that has a cardinality relatively near to the maximum clique. Of course, these are faster algorithms. Just to take two examples, you can find online a relatively efficient complete algorithm, which is clicker. And to make the more easy example of a heuristic algorithm, you can quote the greedy algorithm. That means you choose at random a points, then you see his neighbors, then you choose at random a new point in the neighbors, then you see the neighbors of both points, and so on, and you finish in the end. Typically, for random graphs, you finish on a clique that is much smaller than the maximum clique. Roughly is the alpha as a cardinality that is the alpha of the maximum clique. So you would like to see more efficient algorithms. Then the idea that I want to discuss in the talk is to use ideas of the statistical mechanics to try to solve heuristically this optimization problem. the configuration on the graph, the instances, are the configuration in statistical mechanics. In general, in the optimization problem, you have a cost function, and in this case, in the statistical mechanic approach, this is the Hamiltonian. And in fact, if you want to optimize the problem, you are looking for the ground states of the Hamiltonian. And in fact, the ground states of the Hamiltonian are the configuration where the Gibbs measure is concentrated when the temperature is very small. So a possible idea to solve heuristically the clique problem is sampling from the Gibbs measure of the statistical mechanic translation of the clique problem. Well, but this slide, in fact, is a explanation of the title of the workshop. So maybe I can skip it. I mean, you look for a microchain which is ergodic and for which the reversible measure is a Gibbs measure, and then the ergodic model, the ergodic theorem guarantees you that the after n steps the distribution tends to the stationary one, and hence a possible way to find a heuristic of the maximum clique is to start from a configuration to define Markov chain, and then to run it for a sufficient long time. And sufficient long time is, of course, with quoting, because this is the problem. And then to hope that the final state is a sampling of the stationary measure. As we all know, the main difficulty is the fact that the evolution is trapped in metastable states, and this may imply that the sufficiently long time is very, very long. And this is the definition of the mixing time. So I think I can skip this slide. Well, an example of the statistical mechanical approach to the clique problem is an algorithm that was studied, I don't know the year, I don't remember, in the 80s by Mike Jerome, and for which he found, in fact, a negative result in the sense that I'll present you in a moment. And the algorithm is the following. The space state of the Markov chain is a space of all the clique of the graph. So the algorithm moves on feasible states. And for each clique, the energy is minus the cardinality of the clique. And then the transition probabilities are different from zero only when you do a single spin flip, for configuration that differs just in one point, and the probability to go in the configuration x prime is e to the minus beta times the positive part of the new energy minus the old one. That means that you choose at random a point. If it is already in the clique, you erase it with probability e to the minus beta. If it's not in the clique, but you can add it to the clique because the old configuration plus the new point is a clique, then you add it with probability 1. If not, you try again.
So here by clique you mean complete subgraph, not maximum.
No. Clique is yes. Maximum clique is a maximum clique. A clique is a complete subgraph that can be not maximum. Okay. Note that in the limit of beta that goes to infinity, that means lambda that goes to 0, this is a greedy algorithm that I described before. For these dynamics, Jerome proves that there exist initial states such that you find the clique slightly bigger than the clique that are easy to find, the clique that you find with the greedy algorithm, for example, in a time that is super polynomial in n. The main idea is to study the isoperimetrical constant, and can be explained easily because in fact if you consider a clique of size k that is slightly bigger than logarithm in base b, in this case is 2 of n, and you ask with what probability this can reach a bigger clique without passing from smaller cliques, then this probability is extremely small. Since you have to pass from these gateways if you want to reach a bigger clique, and these gateways are extremely rare, you see that the probability to go to large clique is very small. So so the mixing time of the chain is super polynomial in n. Well, what we tried to study is in fact a similar algorithm. In a limit, the algorithm is the same. But it is an algorithm that can also have not feasible configuration. I mean, you define this Hamiltonian, this cost function, and Jij, the interaction between the sides of the graph, is 1 if the edge is not in the graph, and 0 if it is, and then you want to give a to lower the Hamiltonian the more the configuration is large. And you see that it is easy to prove that this Hamiltonian is minimum on the maximum clique, and clearly it is defined also for configuration that are not cliques. On this Hamiltonian, we define the Glauber dynamics as before, and we tried numerically this algorithm, and well, I'll tell you something about this algorithm, but I'll tell you more about the next algorithm that I will present in a moment. I want to make some short remarks. For when beta is very large and h is very small, but is proportional to 1 over beta, this tends to the dynamics studied by Mark. And hence we tried to generalize the proof of Mark of the fact that you have very slow mixing times. But at the moment we failed, because the problem is that the number, since you have also not feasible states, the number of these states increase very rapidly. So to take in account also the entropy of the problem is difficult. This does not mean that I think that the algorithm is better. I think that it has the same problem, that it has a mixing time that is not polynomial. But for the moment we do not have a proof of this. And surely, since the algorithm is free to arrange it himself in not feasible states, it is possible, as numerically is clear, that for a finite size, for a given size, it gives you a slightly better result than the algorithm that is confined on clique only.
Can you go back for a second? Go back one slide. So the maximum clique problem is the same as the maximum independent set problem.
Yes.
If you go to the complement.
Yes, of course.
And for GN 1/2, I
Yes.
guess they did.
Yes,
the same.
it's exactly the same, but you have to say Jij is 1 if the ij is in the graph and
Right.
Jij is
And
0.
so then this is the lattice. If you go to the independent set version, this is the lattice gas with repulsive interactions and fugacity depending on h.
Yes, but defined on a very strange space because it is a random graph.
Yeah, just defined on a given graph.
Mhm.
And then you're proposing basically the standard metropolis dynamics of inserting or deleting a particle.
Yes.
In this,
Yes.
right?
Yes. But
And
this is
Jerem's algorithm would be this. I mean, Jerem's algorithm would be the same, except
But-
the soft nearest neighbor repulsion becomes an infinite nearest neighbor.
yes. Exactly.
And then you're wondering
in a-
whether
yes.
allowing to go through intermediate
Yes.
states with
Yes.
a finite cost rather than
Yes,
infinite cost.
exactly. In a physical sense, this is exactly true. May I go ahead? Well, this is a remark on the physical analogous of. I mean, this Hamiltonian is, from a graphical point of view, is the same of the Sherrington-Kirkpatrick, the spin glass model. But there are a lot of differences, and then the ideas of the replica trick and so on and so forth give only trivial facts for this Hamiltonian, and this is a list of differences, but maybe it's not very interesting. So I'll go to the next. To the next slide, and I want to tell you something about another algorithm that was inspired by the spin glass theory, and is the following: you start from a configuration, and you compute the field that a particle in a site I feels from the particle in the configuration. If you want, in other term, this term is counting the number of missing links from the site I that you are considering and the configuration where the system is. And this is an additional weight that you have to add in order to have the minimum on the cliques and not on say different sets like the bipartite complete subgraphs. Another important difference of this algorithm is that it works on the canonical ensemble. You fix the number of points that you put in the configuration. Then you define this new Hamiltonian that is in fact the same as before, except for the fact that in the dynamics you start from a configuration sigma and you find the distribution, you sample sigma prime according the distribution given by this Hamiltonian. And there is these additional terms that tells you pay if you move from the configuration where you was, because this is the overlapping of the two configurations. There is the minus sign, so the more the configuration are different, the more you pay.
So as a function of sigma prime,
yes,
this is the sum of the energies that individual particles of sigma prime would feel
with
if they're sitting in a bath of everybody else being sigma.
Yes.
And then you've added this extra overlap.
Yes, exactly. Then the microchain that we studied is exactly to say the probability to go from sigma to sigma prime is proportional to e to the minus beta times this Hamiltonian. Well, we are able to construct the algorithm is trivial. You start from a given random configuration sigma with k sites. Then you compute the cavity field. If there are k vertices with the cavity field equal to 0, you found a clique. If not, you choose a new configuration, sampling at random configuration with a product distribution with the relative weights given by the Gibbs factor for the cavity field. To sample this distribution, if beta is very large, you have to choose the k sites with the lower cavity field. If beta is finite, you can do the sample with the Kawasaki dynamics, which is very fast in this case. The sampling of the single step of the Markov chain is very fast because this is a product measure. So it is, yes.
Just k 1 plus epsilon log n. K is the size of the subset.
Excuse me.
K.
No.
What is fixed?
K is fixed.
And that's the number of particles.
Yes. Well, I'll tell you something about what we did. In fact, you try to find. This is an algorithm to give an answer to the question: are there cliques with cardinality k, size k? Yes. This is.
We just ask the question. Aside from the fact that k is fixed, this is basically applying the heat bath algorithm in parallel to all the vertices of the lattice, even though those updates can't really be made independently. So this doesn't leave invariant the ordinary Gibbs measure, right?
No,
you don't even know what measure this leaves invariant.
Yes. No, I know. I'll show you in a moment. What we know is that the chain is ergodic. This is easy. In fact, the important thing is that this is a collective Markov chain. You may change even the whole configuration in a single step, and you have a non-zero probability to go from any configuration to any configuration in the fixed number of sites space. Then the stationary measure is this sum over all configuration of v to the is proportional to sum over all configuration of v to minus beta h of sigma tau. And it's easy to see that if beta is sufficiently large, you have that this measure is concentrated on cliques.
So this really ought to be thought of, I think, as a reversible Markov chain.
Yes,
on
it is.
Pairs of configurations, and you alternately update one element of the pair fixing the other. And then it's a reversible Markov chain with respect to the Hamiltonian h of sigma and tau.
Yes, if you want to, you can say this. Well, another important fact is that for beta very large, the energy of the couple of configuration decrease along the path. This helps to understand something. Well, I'll tell you something I'm running out of time. I see. Well, so no, I'll skip this part on Fermi statistic. I just want to there are numerical results. Maybe I'll show you the numerical result if you are interested later. What I want to say is just an important thing that we understand is the following. You have the sites that are in the configuration and the sites that are outside the configuration. The distribution of the cavity field of the sites inside the configuration is a difficult problem, and we do not have general result on it. But it's clear that the site outside the configuration have a distribution of the cavity field that is binomial, because each edge is there with probability independent, and so the distribution is binomial. After a while, since the energy decrease, after a while you see a certain distribution of the sites that are in sigma, and then a binomial distribution. Well, the fact that we realize studying this binomial distribution is that there is this gap between the two. But this gap appears when the graphs are very large. You have a gap of order 1 for graphs with 8,000 vertices. So what I want to say is that if you want to exit from a trap of this is, if this is sigma, the distribution from which you start, this is a trap because you tend to stay on sigma. But the gap to choose at random with this law a new vertex is very small, up to size relatively big of graphs. This is the reason why we see that you obtain very good result in a reasonable time with this algorithm for graphs that are relatively big. I mean bigger than the Dymax benchmarks or things like this. I'm sorry. Well, I think I finished.
Any questions?
So, again, as you vary k, are there values of k where you can...
Well, yes. What we did is to fix a random graph and then to increase k. Clearly, to find the maximum clique, this is slower than Glauber dynamics, of course. So you have to take in account that the time are longer. But in fact, especially for very dense graphs, the performance of this algorithm are better than a simple Glauber dynamics, the Glauber dynamics that I showed before. And you increase k up to the last value on which you find clicks.
Is there any particular reason for running this cavity algorithm at fixed k? I mean, you could also have run exactly the same cavity algorithm with exactly the same joint Hamiltonian h of sigma and sigma prime at variable k.
We tried, but it does not work. We are trying to understand why it does not work. The fact that you have to add points even if they are not completely connected force the algorithm to move and to sniff around. If you have a variable number of sites, clearly the algorithm build a clique that is in general is quite small. Then add some new particle, but it's very difficult that the clique increase. We are studying this problem. Probably you would need a fugacity that depends on the configuration, but this, from a numerical point of view, is very heavy. So it does not work, or at least for the moment, I have to say that it does not work.
Have you tried this for non-random graphs?
Well, we in the numerical runs that we did, we ran it for a number of steps of the Markov chain proportional to the number of vertex of the graph, and this means that the computational complexity is n squared times k, so n squared log n. So I mean you can run with the algorithm if you are patient, even very big graphs. So because the computational time grows not so fast.
I was wondering, do you know how, I mean, experimentally, how large independent sets it finds if you try it out on, well, structured graphs, for example?
And I'm sorry.
So if the graph where you're trying to find an independent set
Yes.
is a structured graph of some kind, do you know how well you will do there?
You mean? No,
Instead of using random graph
Yes.
as your input,
Ah.
use some other
Sorry. Well, we tried the algorithm on the Dymax benchmarks that are not only random graphs, and it found the maximum clique known for 58 out to 69, something like this. So it works quite well. There are the Brock instances in the Dymax benchmarks that are difficult, but I realized that they are difficult for everybody. So okay.
Hey, thanks again.